All right, so this is a video on using the washer method to find the volume of a solid of revolution. So the washer method is different than the disk method because what we're going to have is two functions as shown here. So we have the upper function, f of x, the lower function, g of x. And if we were just to do a solid of revolution on the upper function, it would kind of look like a cup with a flat bottom and a curved side, and a very thin, actually just would be a solid. There's no space inside it. So it's just a block that looks like a cup but has no hole. What we're doing here is we're actually just rotating this amount. So there's going to be a void in the middle of that cup. So it's really going to end up looking like, this is really not a great visual of it, but there'll be a cone missing from the inside. Okay, so the way it works is we rotate. Here's the same graph here, but it's kind of visualized and rotated. We end up taking the distance between the two functions and we rotate those around. Now the first one, since it's the lower function is 0, we're subtracting 0 from the upper function, so that ends up being a full circle. And the very outside edge, the functions are both at 4, so there's no distance between them, so this is just an open ring. Okay, so there's no volume there. But in between, each of these spaces would form a cross section that looks like this shape. It looks like a ring, okay, but it's called a washer. There's an outer radius and an inner radius, and to find the area of that, we're going to use the formula pi times radius squared minus radius squared. Notice capital and lowercase. The capital is the larger radius. The lowercase is the lower radius. When we incorporate that into calculus, we get the above formula. Volume equals pi from a to b of the upper function squared minus the lower function squared dx. Now this is all rotated around the x-axis. Okay, so on this particular problem, I think I definitely did that wrong. That should be a 4 there. So what I'm going to do is just change some values here. So we'll call that 4, 0 to 4. We're going to evaluate that down below. 4 here. I have to square this binomial. I end up with x plus 2 root x plus 1. I have to square 3/4 x. So I square the 3, I square the 4, I square the x. And then I have my function that I will find the antiderivative of. Each piece. Oops, missed one. Okay, and then I'm going to plug in my 4. And since there's no constant term, 0 yields 0. So I'm not going to worry about the subtract 0 piece. So I've got some recalculating to do here. 4 there, 4 there, 4 there, 4 there. Boy, I did a lot of work for nothing down here. So, pi times 16 times half is 8. That's a nice one. 4 to the third is 64. The square root is 8. So 8 times 4 is 32 thirds. Plus 4. This is 64 divided by 16, which would be 4. So it's minus 12. So that's 12. So we end up getting 32 pi over 3. There's your first washer problem example. Let's look at the next one. Okay, we got two curves this time instead of a curve and a line. The top curve is g of x, which is 2 root x. The bottom curve is 1/4 x to the 4th. And we're going to find the area from 0 to 4, rotating around the x-axis. So just a visual here, it ends up being kind of a bowl-shaped outer area or outer surface, and then inside is kind of a curved funnel-shaped void. What we're looking at is the outer radius is going to be the upper function here. So that would be g of x. So this is a little different than the last problem. We're going to put g of x first and subtract f of x afterwards. So we're going to square g of x. So 2 squared and root x squared gives me 4x. We're going to square f of x, square the 1/4, and square this x squared. So we get 116x to the 4th. We integrate. We have a 0 and a 4. And then we keep the pi on the outside. We evaluate. 4 in here. 4 in here. That's 32. This ends up being 64 over 5 when you reduce it down. And 160 minus 64 is 96. Keep the pi, keep the 5. 96 pi over 5. So if you understood the disk method, then you're probably looking at this and saying, I can figure this out. So block 4, I want you to stop there. Block 3, though, I want you to take a look at this problem. And it's really the same exact problem. However, we're going to rotate around the y-axis. Okay, so it basically inverts the shape. Just a reminder, we need to change the functions to be in terms of y. So instead of f of x, I put y. So it's y equals 1/4 x squared. I solve for x, which we would multiply by 4 and then take the square root. We end up with 2 root y equals x. And then 2x, so y equals 2x, divide by 2, and then square both sides. I end up with 1/4 y squared equals x. The difference now, though, is if I look at the outer function, it is now y equals 1/4 x squared, even though it's in terms of y, which is this equation. So when I look at this one, again, here's the shape. It's just kind of flipped on its side. We're going to square the 2 root y. We're going to square the 1/4 y squared. And it's in terms of y, so we're going from 0 to 4 again, because it starts at 0 and ends at 4. And then all of the calculus is the same. So we're going to end up with the exact same answer as the previous problem. And I'm going to ask you why. I want you to pause, think about it, and we're going to discuss. So here's the reason. Okay, when I found each function in terms of y, I got the other function, which means they are inverse functions of each other. And that's why when you do the y-axis versus the x-axis, you end up with exactly the same shape in just a rotated fashion. It's not always going to work out that way. So I just wanted to point that out.